So hello everybody, good morning and welcome to this new session of the Escape Summer School. So today's session is going to be a first library presentation with Tamas Gal. And I will just give the word to Tamas and I'll let him present. So you have, okay, all for you, Tamas. Thanks.
All right, many thanks. I hope my microphone is working correctly. I forgot to check. All right, so let's begin. Yeah, this is a Python talk. So actually, yes, as Enrique said, it's about Python libraries, but also about Python itself and the internals of Python. And I set up a live poll which you can participate on during the talk. So you can either scan this QR code with your mobile phone or just type in this address, which we will also see on the footer of each slide. So I will just start this poll right now and you will see the live updates if you participated. Yeah, so let's start. So this is, as I said, an overview talk. I will give you a short introduction to Python. Then I will talk a bit about the basic internals of Python. And then we will have a look at some libraries and tools which are useful in a scientific context and highlight some nice things which we will also explore during the next days and next week, etc. So you might ask, who is this clown? So I would like to introduce myself first very quickly. So my name is Tamas Gal. You can just call me Tom. I was born in 1985 in Debrecen. This is Hungary. And I'm an astroparticle physicist working at the LNS Center for Astroparticle Physics, also called ECAP. And my main working area is the KM3net neutrino detector, which I'm working on for several years now. I think it's now 9 years, maybe 8 years, something like this. And also, I also work on open science and data. So I try to make tools and infrastructures, build infrastructures with other nice scientists who try to make science open. I'm also a sysadmin doing DevOps at ECAP, which includes also the ECAP and the KM3net IT services, so continuous integration, GitLab administration, and all kinds of stuff. And my programming background is, well, I started somewhere around 1993 on Amiga. And the first real application was a toilet manager with tons of go-tos. Yeah, nowadays I mostly use Python and Julia and JavaScript and C, C++, Objective-C for work, Haskell for fun. But I also know a lot of other languages as usual. If you're interested in computer science, also you have to learn a lot of languages to get impact from different paradigms, etc. My favorite editor is Vim. I used it for 23 years, but I switched last year to Emacs with the Vim mode. So it's basically still Vim, but in my opinion, it's the better editor because there's always this question about editors. And otherwise, I love adventure motorbikes, climbing, electronics, modular synthesizers, and DIY stuff. Okay, so I think that's enough. Let's start with our main topic. Feel free to contact me about whatever you like to talk in Slack, etc. So Python. Okay, so I see at the poll a lot of people are using Python. That's great, of course. You have also some C++ users and some Fortran users. It's also nice. And Matlab, of course, very present. So let's talk a little bit about Python, and in the next poll, you can tell me when you started using Python. So Python is a programming language, of course. It's an interpreted high-level general-purpose programming language. This is how it's called. It's mainly object-oriented, but it has a lot of other paradigms which you can work with. So procedural, imperative, functional, structured, reflective, etc. So it's a very, very general-purpose thing. It's dynamically typed and garbage collected, so we will talk about this later. It was designed by Guido Farroso, and it has this main philosophy of batteries included. So it's quite nice when you install Python, you get a lot of things already included and can solve a lot of problems. And it also tries to avoid premature optimization. So this is also one of the main design philosophies. So this means that that Python users always try to move time-critical functions to extension modules written in faster languages like C or Fortran. So brief history of Python. The rough idea came up in the late 80s. and it meant to descend the ABC language, which has a lot of ideas which were transferred to Python later. And it should basically fill the gap between something like C and Shell. So it should be close, or at least performant, or highly configurable, but also easy to use as a shell script. So the first line of code of Python was written by Guido van Rossum in December 1989. I think he did this over the Christmas holidays, the first developments. And after 1 year of development, it was released as open source. Well, open source in that time was not really a word, but it was basically released. And version 2.0 came out in October 2000, and version 3.0 in 2008. And actually in July 2018, Guido van Rossum resigned from his BDFL. This is how he's called, the Benevolent Dictator for Life position. So, but he's still working on it. And 2020, Python 2.7 finally ended the life. So it has an end of life date. It was basically outdated. And the current stable version is now 3.95. Which we will also use in this course, or 3.9 at least. Okay, the Zen of Python, it's probably quite important. If you launch Python on your computer and just hit import this, you will get this nice text, which is written by Tim Peters. And this basically combines consolidates all the design philosophies which are driving Python people. So you can read it on your own. It's always nice to just read it here and there to get reminded how to write beautiful code or how to program things. Beautiful is better than ugly, explicit is better than implicit, etc. So every kind of every single line here has really benefits. You should know about this. Okay, let's talk about the popular languages. This is the TIOBE Programming Community Index. This shows the popularity of programming languages over time. So this started in 2002. And this is basically something like, so what they do is they analyze Google search results and other search results for keywords related to the programming language itself, something like Python tutorial or C tutorial, etc. And then they count the hits and do some ratings, etc. Yeah, and Python, as you can see, this is this black line is now the second most popular language according to TIOBE, and has beaten even Java and C++. So on the next slide, you can see its popularity. It was also the programming language of the year in 2007, 2010, 2018, and 2020. So this is basically how much rankings it got up over the year. And yeah, there's a nice increase, which started somewhere around 2016, 2017, 2018. I call this the era of machine learning, where things really went off. And a lot of machine learning libraries got some nice Python interfaces. So these were, of course, picked up by many, many people. And I think this is quite a huge impact on the popularity of Python. Okay, so your journey through Python, this is just, I did this always in this school. So this is the 4th time I attend to this school as a tutor. And what we did is basically, we asked people if they can answer these questions or with yes or no, and just keep their hands up to see how experienced they are. In this case, you can just use the poll. Let me check. Oh, so it's quite evenly distributed. That's really nice. And there are also some hardcore Python users here. So let me switch to the next one. So what is your Python level? So it begins with the Explorer level. So have you ever launched a Python interpreter? Have you ever wrote for while loops or if-else statements in Python, or your own functions or classes or list dictionaries, set comprehensions? And do you know what a generator is? Then you are probably already in the intermediate stuff. Have you ever implemented a decorator? This means that you are probably more advanced, a meta class, a C extension, etc. Or, and the last question is always fun to talk about, is do you know and can you explain the output of the following line for Python? So here we print 5 is 7 minus 2 and 300 is 302 minus 2. So this is quite interesting. If you know this, then you probably know a lot of about Python internals. So this is this are you kidding me section, or I called it in the poll, I am the next BDFL. So let's have a look at this. The answer to print 5 is 7 minus 2, and 300 is 302 minus 2. So you probably know this is compared. This is thing. This basically compares if those are the same objects in memory. And if you launch this in Python 2.7, you get true and false. So for 5, you get a true, and for 300, you get a false. Although these are both the same numbers. Python 3.6 is the same, but 3.7 it's suddenly true and true, and also in 3.8, but now you get warnings, and in 3.9 you also get warnings. So now, of course, you ask yourself, does it make sense? What is happening here? And to understand this, we have to take a look at the source code, or at least I did this for you, and I can explain what's happening. So there is this Py object constructor, this Py long from long. This takes a number, and this returns a new reference. And the funny thing about this function is that the current implementation, so it's valid for all the Python versions until now, keep an array of integer objects for all values between -5 and 256. And this means that these values are pre-cached for you. So whenever you create an object, which is so a number, basically, which will be represented as an object, as we will see later, between -5 and 256, this will always give you the same number if this is in this range. So this is why this is operator gives you a true for this lower number, and 300 is always generated newly. So these are always two different objects, no matter what you do here. However, as you have seen in Python 3.7 and newer versions, this is not the case anymore. But this has another reason. The reason is that the constant folding is moved from the peephole optimizer to the new AST optimizer. This might sound a bit cryptic for you, but what this basically means is that Python already figured out when you launch this line that these are the same numbers, and does some tricks here. You can always also look at this commit if you want to for the more advanced, if you're interested. And here's a small snippet of the source code, where you can see that there's this small ints where you have this pi n small negative ints and pi n small positive ints. So this is the number of negative ints you have, like this -5, -4, etc. until 0, and the positive ints. And this is the container which contains all the pre-allocated values whenever you launch a Python session. Okay. So let's talk about why is Python so popular for science. So as I already said, there is this machine learning thing, but of course, in first place, it's easy to use. It's interactive, which is always great to explore things. And it has a ton of built-in use for supplementary functionalities, as I already mentioned. And because it's a general purpose language, it means that scientists can focus on a single language to rule them all. This is mostly true, but of course it can also go wrong. So that's why I put that can they really focus on a single language. As we will see later, it's unfortunately not really the case. And here's the performance of languages, which I've taken from the Julia language micro benchmarks. So these are really quite small benchmarks, but they are pointing out the performance of some languages. So on the left side, you can see C, which is the reference implementation. So all the stuff, all the benchmarks are first run on C, and this is then your 1. And then you have different languages like Julia, LuaJIT, Rust, Go, Fortran, Java, JavaScript, MATLAB, Mathematica, Python, R, and Octave. So here's Python. And you measure the time it takes to launch these applications, like an iteration of PySum or matrix multiply, matrix statistics, parse integers, etc., etc. And as you can see, in case of Python, the spread is quite huge. So there are some stuff like this matrix multiplication, which is very close to C. This is because Python is using some C or Fortran code to do these matrix multiplications. But some things cannot be done with these standard libraries, or at least with these common libraries, and has to be done in Python. And those are slower. So you get an order or 2 orders of magnitude difference in contrast to C or Julia or Lua, Rust, Go, or other compiled languages. And this is why we have to take care about performance. So let's have a look at the basic Python internals to understand these performance issues Python have. And for this, I would like to talk about how a source code is basically converted into runtime. And this is what basically happens on your machine when you launch a Python program. You have the source code. I call this here foo.py. And then you have this compiler. And the compiler will create these PyC files. So this basically contains bytecode, which then can be interpreted by the Python interpreter. So it's not actually the case that this source file gets interpreted. Many people think that they are writing a script and this is just get interpreted. But in fact, it's first compiled into this bytecode, and these are byte instructions, as we will see later. This is then interpreted, and then you reach the runtime. So let's look at the bytecode. I will take the example from before for Python 3.6, where we have this call print 5 is 7 minus 2 and 300 is 302 minus 2. And if you compile this, so I used here this module, which is basically the disassembler module. And you can compile and then look at the bytecode with this command. So you can see that it loads a name print because it will call this function print. It will load two constants, namely this 5 and the 7 minus 2. And then the compare op, which is this is, then another two constants, etc. Then it calls the function and prints the statement. So everything is fine here. And in Python 3.7, it looks quite similar, but there is a tiny and important difference. If you look at this load const op command, this will put things into a tuple to save it later. This is called co-consts. These are basically the compiler constants, if you want to call them like this. And these values are basically kept in this array, and then the operation is done with them. And if you, the same, of course, for Python 3.7. But if you look closely, the op arg, which is the argument you pass to this op command, tells you where to put these things in. So in case of Python 3.6, these values land in different positions in this co-const. So the first one is put in the 0, and the second one is put at the 6th position. And here a 3 and 7 is taken. And as I told you, the numbers between -5 and -2 and then 256 are pre-cached for you. So they are occupying two different places. But in this case, for the 5, they are still pointing to the same piece of memory. So this is why the is operator returns true. In this case, these are two different objects and are also standing at different places. Now in Python 3.7, the constant folding takes place. So it figured out that you are using the same value, so it puts them at this very same location. So in this case, you will always get an equal because they are sitting in the same position. So I hope now you understand this. Oh yeah, I forgot to highlight this. So now I told you that this is putting something somewhere and something is put into memory. This now sounds a bit weird. I'm not sure about how much you understand about the memory structure or how code is or how objects are passed around from heap to memory. But I would like to try to explain to you. So the type of a Py object, this is a quite funny thing. This is actually in the source code of object.h. So it means an object has a type that determines what it represents and what kind of data it contains. So for example, you can have a type PyInteger. So it determines that it's an integer and it contains an integer. And an object's type is fixed when it is created. So whenever you create an object in Python, it has a fixed type. And types themselves are represented as objects. So the type itself is also an object. And the type itself has a pointer pointing to the object representing to the type, which contains a pointer to itself. Yeah, this is a bit confusing, and it's even more confusing if you look at what, for example, 42 is represented by in Python. So you can call this dir function to 42, which will list all kinds of methods you can call to this. So you would think that 42 is just a single number. Maybe you have a 64, or probably you have a 64-bit computer. So it's only represented by 64 bits in this case. But in reality, this is a PyInt object, as I have already said. It has a type, which is a pointer to this PyType object. And it also has a reference count, which is used for counting if the object still lives or not. So this is for memory management, which is garbage collected in case of Python. And then here sits our value with the 64 bits. So actually, this is a huge thing in memory. So it's not really just the 64, but it has another pointer with 64, another pointer with 64, on another reference count, and then a pointer to another stuff. And you can also see that it's subclasses from this Py object, which also has a type, which also points to Py types. So everything is connected here, and everything is kind of blown up. Yeah, so this is about the memory. Now, about the performance, like the CPU stuff, what about this? This is your best friend and probably worst enemy if you do high performance computing. This is the global interpreter lock. This is how it's called, or the GIL. And the GIL is basically something which they introduced in Python to make things easier, I would say. It prevents parallel execution of bytecode, which basically completely eliminates the possibilities to write Python pure code, which is executed in parallel on different threads or different CPUs. So even though Python has real threads, which is not really true for all the languages we have, they never execute code at the very same time. So this is very important to note. And this is also the reason why we have to work around this stuff with different kind of libraries, etc. So you have context switching, this is how it's called, between threads, which creates overhead. So, and also the user cannot control thread priority. So you are basically, if you are doing multi-threading in Python, you completely leave it up to Python when to switch these contexts. And this means that threads perform really badly when you do CPU-bound tasks. It's really nice if you mix it with IO-heavy tasks, but if you are really hitting on the CPU, then this context switching will be extremely bad for your performance. So here's an example how to visualize this a little bit. So this is a single thread function which I wrote. It just counts to a given number. So here in this case, I pass in. Oh, I forgot to put in some dividers. It's 100 million. So I just count down from 100 million until I reach 0. And I measure the time, how long it takes for Python to do this. Yeah, and as you can see, it takes like 7.5 seconds. And if I use threads, and then here I just use the trick that I open 2 threads and I count from the half of it down. So it basically runs in parallel. I count down from 50 million 2 times in parallel. And I measure the time, I get something like 9 seconds. So it's even slower than using a single thread. And this is, of course, probably not what you have expected first, but as I told you, there is context switching, which creates an overhead, and we can even look at it. There is a very, very nice analysis done by David and Beasley. You can go to this link if you like and explore it in more detail. So he has run this in Python 2.6. It's still valid for newer Python versions. What you can see here is the green stuff represents work. And every time it basically switches the lane, it means that it's running on a different thread. And as you can see, at no single time during this execution, you will see works on multiple threads in parallel. So you are always hopping from one thread to another. And this is what creates this overhead. It can even be worse when you do a lot of calculations. So as I said, this is completely up to Python to decide when to switch these threads. So always think about this. And now you might ask, okay, huge overhead for every single object. There is no real parallel execution of code. How should Python ever compete with all those super fast C and Fortran libraries? Well, it's possible. And the answer is extensions and interfacing to other languages, which are faster, like C and C++ and Fortran. This is what I mentioned at the beginning. We try to do this thing where we optimize later. So we write Python code, and we need more, if we need more speed, we use extension modules. Those are, namely, those can release the GIL and do the heavy stuff in the background, also multi-threaded. All right. So let's do a very, very dumb speed comparison. I usually don't like this kind of stuff because it doesn't reflect real world stuff. But for this demonstration purpose, it's really nice. So you have this pure Python function which calculates the mean of 1 million numbers. So what I did here is I purposely called sum and not NumPy sum or whatever. So it's really just pure Python. It sums up the numbers and divides it by the length of the numbers, which will give you the mean. And if I time it, I get something like 8 milliseconds, which is quite okay, I guess. But if I do this with NumPy, so here I generated an array with 1 million random elements and calculate the mean, you can see that it's much faster. It's already 13 times faster. And there are other tools like Numba, which can do just-in-time compilations. And in this case, I just wrote the function by myself in just Python code, just a dump for loop and return the result. And yeah, it takes 1 millisecond, which is 8 times faster compared to the original Python. But you don't have to know some, well, extra functions. You can just write down your algorithm, which is usually not the case, or not what you should do in Python. And yeah, if you look at, for example, the Julia implementation, which I also like to show because it's very close to the Python syntax, you can see that it's well, quite close to NumPy. So it takes around half a millisecond. Okay, so there are some crazy LLVM compiler optimizations which can take place. So the Numba example, which I showed to you, where I wrote this Python function and just put some funny decorator thing at the top, is a so-called LLVM JIT compiler. So this basically takes your function, your Python function, and compiles it into a really high-performance machine code. So let's see what happens if we sum up numbers from 0 to 100 million. This takes with NumPy, with this very dumb function, around 7.5 seconds. If I do this with NumPy, so here I just created this these numbers in advance, and I just call this NumPy sum. It's already 80 times faster. If I do it with Numba, I somehow get a ridiculously fast result. So it's like 300,000 times faster. And if I go to Julia, it's even more incredible. It's like 7 million times faster than Python. So you might ask yourself, how is this possible? And what happened here is, and this is the reason why I show this to you, is the compiler figured out that what you're doing here is just summing up numbers which are consecutive. And it figured out that it can use the Gaussian formula to calculate the result. So you should always be suspicious when you get readings like this, because if you do a rough back of the envelope calculations, you basically have to do 100 million operations, and you usually count something like a few nanoseconds per operation. You shouldn't reach numbers like in this range. So in this case, you know that some crazy optimizations are going on. So this is possible only if you have static code. In Python, it's much more difficult, as we will see later. Okay. But now let's talk about the Python libraries, which is mostly our main topic today. And yeah, there are a load of libraries out there. And let me start the next poll. So, okay, we have some novice and intermediate users. That's really nice. I hope you all learn something new. Oh, and I forgot to ask you about threads. So let's do this poll quickly before we go to the next poll. And yeah, so let's talk about these Python libraries. So there's this NumFocus thing, which is an organization. They are spending a lot of money on, so they're basically helping out in developing all these nice tools we are using. So I will cover a few of these today, just roughly, like Pandas and NumPy, Matplotlib, SymPy, and IPython. So this is basically the SciPy stack. And there's this Jupyter thing, Astropy, which we will also cover. So most of these are also covered in separate courses. And not part of NumFocus, but also covered in this talk is Numba, NumExpr, and Awkward Array. And yeah, there's of course also Julia, which I love, and a lot of other things. So this is basically your toolbox as a scientist. And I'm not mentioning here any kinds of machine learning stuff, or this is another topic, but of course you probably heard of TensorFlow and PyTorch and all this stuff. Okay, so let's have a look at SciPy, which is probably very useful for many of us. Okay, so there are already people who manage threads. So like, okay, that's nice. So let's go to the next talk. I would like to know which what kind to the next poll. Sorry, what kind of libraries you use. So let's see the SciPy stack. The SciPy stack is so it has some core packages which contain stuff for numerical algorithms, signal processing, optimization, statistics, etc. So NumPy is also part of it. It's Matplotlib, Pandas, as I already told, SymPy, etc. And yeah, so there are also other packages as I mentioned. And the core library consists of many things. So I will just quickly go through these because there are really a lot of stuff. So you have clustering packages to do clustering, to apply clustering algorithms, also constants. So don't define your own constants; they are already constants, so they are somewhere put there out there. Discrete Fourier transforms, etc. Then ODEs, interpolation stuff. A lot of input-output stuff like reading files and then writing files, of course, the linear algebra things, then multi-dimensional image processing, which is really nice, and yeah, a lot of metric stuff and optimization procedures, which are nice for fitting things, etc. And yeah, so as you can see, this is really huge. You most likely will find all kinds of nice stuff to get started off with your analysis before you write your own algorithms. So check this first. And here's just a very tiny example of the SciPy interpolate, which is something which we do all the time as a physicist. You have some data sets, you want to interpolate the data, and then you can call these functions which are coming from SciPy to quickly interpolate the data. Yeah, it's just a very quick example. Okay, but first, let's talk about NumPy, which is, I think, one of the biggest things in Python. This is basically what made Python so successful in the scientific context. And I see that a lot of people are using NumPy and Pandas and Matplotlib. This is really nice. And Astropy, of course, it's a school about astrophysics. So that's nice to see. And there are also upward array users. That's really nice. So we have probably some people from the high energy physics context also. All right, let's check your NumPy level. I'm sorry, to drink a little bit. So NumPy. So this is the fundamental package for scientific computing with Python. And what it gives you is basically a powerful n-dimensional array object, which is called this ND array. And it has nice broadcasting functions, so you can work with these arrays and merge them together and do things with them. It has tools for integrating C and C++ and Fortran. And it has also a lot of functionalities with linear algebra, Fourier transforms, and random number capabilities. And yeah, as I said, most of the scientific libraries build up on NumPy. So it's the basis for all this stuff. And I see that we are quite intermediate with NumPy, at least in the user section, which is also nice. So let's have a look at this for all the people who don't know what an array is. So this is an array which I just created with this arrange function. It creates just an array of 6 elements starting from 0. And it has a dimension, which is in this case 1, because it's one-dimensional array, and the shape, which contains only one element. It's a tuple. And the shape gives you the length, basically, in each dimensions. In this case, we have only one dimension. And this is how it looks like. So this is really how it looks like in memory. So in contrast to Python, where I told you that this Python integer is stored as a pointer, and then there's a reference count, and there is somewhere the value stored in memory. Maybe it even contains a container, a pointer to another place in the memory. In this case, the array itself is an object. So this has a place somewhere in the memory. And this points to this section in the memory, and this is really something which is contiguous. So this means that whenever the computer wants to use this, it only needs to start, and after that, it knows that it just has to jump one memory address at a time to reach the next element. So by memory address, I mean depending on the type of this array, it can be like 64 bits jumps or only 4 bits jumps, etc., etc. So it has a C and Fortran compatible memory layout, which means that you can pass these arrays back and forth between these libraries, which is really cool because you can create your NumPy arrays and then pass them to some libraries which are written in C and C++, and they understand those. And the results which are coming back can also be interpreted by NumPy. So you can do your high-level stuff in NumPy and pass them to these high-performance libraries. So there are array operations and universal functions which you can use. We will explore this later on today. You can see that I can take this array and just multiply it by 23, and it will just multiply it element-wise. I can also square it, or I can use a ufunc, like this exponential function, which can take this array and do this element-wise. Basically, I can put it in this function a single number or an array of any dimension, and it will know what to do. Or you have to tell it explicitly what to do. Another nice thing in NumPy is the reshaping. So you can have your arrays sitting in memory like this from the example before. And now maybe you want to have this in two-dimensional, like 1, 2, 3, and 4, 5, 6 would be in another dimension. You can do this reshape thing, and this will give you the result. So I split it in half at this point. And the nice thing is that there is no rearrangement of the elements in memory. So in fact, the computer does nothing in the memory with these numbers. It only adjusts some internal iterator limits to tell NumPy to jump to the next dimension whenever it reaches this limit. So this is really cool because it's extremely fast. So here also you can have a look if I create an array with 10 million entries, and I time how long it takes to reshape it into a completely different shape. It only takes a few hundred nanoseconds. And as I told you already, an operation is somewhere around the nanosecond range. So these are only just a few hundred operations which were executed, because of course Python also has some overhead, etc. So, but it's really not something like reallocating memory, which takes a lot of time, and copying values over the memory here and there. Okay, so we will discover this later in the NumPy hands-on session and how to deal with this. Okay, so let's go to Matplotlib. Matplotlib is, of course, very important if you want to visualize things in science, which is how we communicate results usually. And Matplotlib is a plotting library which produces publication quality figures in a variety of hard copy formats and interactive environments. It integrates very well with IPython and Jupyter, and it contains all kinds of stuff like this histograms, power spectra, bar charts, arrow charts, etc. And you have full control of line styles, font properties, and axis properties, etc. And the easiest way to get started is probably just browsing its wonderful gallery full of thumbnails and just copy paste them. So this is how I got used to NumPy many years ago. I just went to this gallery, and if I wanted to create something, I just scrolled through and looked at things which look kind of similar of what I wanted to do with my data. And you really can just copy paste them nowadays, put them in a notebook and just apply it to your data. So it's a really good way to learn it. Not all the examples follow the best practices. So here we'll notice that there are some style differences. And here's a tiny example how it's, this is, I think, taken from the example. So I just copy pasted the code, pasted it here, and it worked out of the box. So whenever you want something like this, then just take it and modify it according to your needs. And here's another nice colorful example to do some scatter plots. Okay, now let's talk about Pandas. So we have a lot of intermediate users of NumPy. That's great. Let's see how it is with Pandas. We will also have a small introduction course today with Pandas, where we explore the basics of it. So what is Pandas? For everyone who doesn't know Pandas, Pandas is a Python data analysis library, which is inspired by the data frames in R. So if you are familiar with R, you may have heard about this before. So this is what you get in Pandas also. It gives you this data frame, as I told you already. It's basically a database-like handling of data. And it integrates really well with NumPy and also wraps a little bit of the Matplotlib API. So it's for exploratory work. It's really nice. You can it has a huge number of I/O related functions to parse data. So you can read CSV, HD5, SQL, Feather, JSON, whatever, Excel tables, HTML tables. It understands really a lot of things. So it's a really powerful tool to have in your pocket. You can quickly open things and do operations on them and do real data science. So this is basically the data frame, which is the main thing around Pandas. It's a table-like structure, and you can access elements by row and column, and you can group them, you can join them, and do all kinds of stuff. So in this case, I just opened a file, which is an event file from one of our detectors, and it's just some dummy data, but it looks like data from our detectors. And yeah, you can see that it's also really nicely printed in this Jupyter notebook like a table. So it has also some eye candy to make your life easier when working with this stuff. As I said, there are lots of functions to allow filtering and manipulating and aggregating the data to fit your needs. Like in this case, I create a pivot table on the event ID and on the values of the DOM ID, and also pass an aggregation function to it. So yeah, we will talk about this later. Don't be confused. It's a nice tool. And then PyTables, another very useful library. So you probably have heard of HDF5 before. I also have a poll about this later. So PyTables, this gives you an interface to the HDF5 implementation. And this is also a database-like approach to data storage, so to say. It has some features for indexing and in-kernel and fast in-kernel queries. So this means that you can write basically your database operations and apply to HDF5 files and get the data back you want. And it has a custom system to represent data types, which is kind of nice. It's not the most performant one. I will come to this later, but very, very easy to use. And it's also used in Pandas as an HDF5 IO backend. So what it basically does is on the upper left side, you can see your mouse, I hope. You can see that I create a NumPy array here, and I can use tables, which is imported as TB here. I can just ad hoc create this foo.h5 file in write mode, and I create a table inside this file, and I dump into this file my data and append it. And then it's saved. So this data, which I created here, can then be opened by any other application or library or whatever, which has access to some kind of HDF5 IO. And in Julia, there is the HDF5 package which you can use. So you can see that I created it in Python with PyTables, and I can read it in Julia, and I get the very same results back. Yeah, so this is really nice to exchange data with others, and I encourage you to explore it. If you are working a lot with huge data and you find yourself dealing with gigabytes of CSV data, then maybe HDF5 or probably HDF5 is a good option. There's also another HDF5 library which is very, very useful. It's called H5Py. It is not as performant as it is not as. Oh, I have a question. Sorry. Let me check my. Someone pinged me. Oh no, it wasn't. Okay, now let's continue. PyTable. So PyTables is a more Pythonic way, and H5Py is a more low-level alternative HDF5 wrapper. It feels. Oh, it feels more Pythonic than PyTables. It's not really. It's the other way around. So PyTables feels more Pythonic. H5Py is more low-level. It maps the HDF5 feature set to NumPy as closely as possible. So this is why it's a bit more advanced. You have to know a bit more about data types, etc. But it's a good thing anyways. So I would recommend to check it out if you want to do something which is lightweight and extremely highly performant. So here also the example how to create the data set. So as you can see, this is really not that different. The commands are a bit different, but if you go into more details, it's really different compared to PyTables. So on the upper side, I created a data set with H5Py. And on the lower side, I opened it in Julia. And as you can see, the data is the same. OK, now coming to Numba. I already told you a little bit about Numba before when I did this micro benchmarks. So Numba is a JIT LLVM compiler for Python. I already told what JIT means, but I think I did not explain it a bit further. So JIT means just in time compiled, and LLVM is the compiler they're using. So just I think I have let's continue. I have a slide about this. So Numba is a compiler for Python array and numerical for Python array and numerical functions. It gives you the power to speed up code written directly in Python. So it uses this LLVM, as I said, to boil down pure Python code to JIT optimized machine code. So we heard earlier that Python uses this compiler to create bytecode, and then this bytecode is interpreted. Numba is very different. I will show this to you later. It only accelerates selected functions decorated by yourself. So this means that Numba is not something like you activate it and everything runs faster. This cannot work, unfortunately. You have to tell Python explicitly which functions should be wrapped into this Numba JIT compiler. And it has this native code generation for CPU and also for GPU. It integrates really nicely with the Python scientific stack, so especially with NumPy, thanks to NumPy. And it runs side by side with regular Python code or third-party C extensions and libraries, which is why I also very like it. It has great CUDA support also if you want to use the GPUs. I mentioned that it is capable of generating GPU code, and it has N-core scalability by releasing the GIL. So yeah, you can do real fun parallel stuff with this. And you can create NumPy universal functions with some nice decorators either. Okay, so let's have a look again at this thing, how Python does the runtime thing from your source code. So as we already have seen, there's our source code, then we have the compiler generates this bytecode, which is some cryptic stuff. And then the interpreter runs this. So yeah, this is basically, so what Numba now does is inside the interpreter, it takes out this control flow graph and the data flow graph and generates a bytecode, an intermediate representation in Numba, which is basically something very specific to Numba. So you can imagine it like this thing now creates another bytecode by interpreting the bytecode from Python. And then it does some type inference. So this means that it tries to figure out the types of the variables you're using. And it creates this typed Numba intermediate representation. This is how it's called. And then this one is lowered and an LLVM intermediate representation is created. So this is the concept of LLVM. So LLVM is basically a compiler, which is very universal. And it's unlike, for example, GCC or other compilers, which take a very specific language and just compile it to runtime. The concept of LLVM is that you can take whatever you want. You only have to pass LLVM intermediate representation to the LLVM compiler, and then the code generation is done by LLVM. So this is how Numba works. Numba tries to figure out what happens inside a Python function, translates it into this LLVM intermediate representation, and then LLVM takes care of it. So the nice thing is you are completely uncoupled of this process, and you're not tying LLVM right into your system. So here is a Numba JIT example. So imagine there is this numbers, which 1 million numbers reshaped into a rectangular thing. And now I do this summing up. So this is just a really dumb function written in pure Python. As you can see, you shouldn't do this at all if you're dealing with millions of elements. So this takes something like 300 milliseconds if you run it in Python. And all I have to do to use Numba is put this @nb.jit at the top of it. And what it does, it takes this function, analyzes this stuff, like I showed it to you on the previous slide, and generates some really high performance machine code given, which is specialized on the type of the thing you are passing in. So it looks at this array which you are passing in. It looks at this D type, and the D type is given by NumPy in this case. And so in this case, these are float 64s. And then it basically knows the type of every single variable inside this function. So it can generate specialized function calls, because the CPU has, of course, specialized functions for all kinds of stuff. It has a specialized function to multiply integers with each other or floats with each other, etc., etc. And if you call them those functions directly, you will get out the most of your computer. So the result is 2 milliseconds. I'm sorry. So this is 135 times faster with a single line of code. So all you have to do is just put this on top of it. So yeah, this is really cool. There is an example for a NumPy vectorized thing. So here I created 2 arrays. Again, 1 million elements. On the second array, I just added 23. And here you can see a bit more complicated thing where I calculate the absolute value of the both values when I subtract them, and then absolute value sum together and then divided all the stuff. So this gives you 23 nanoseconds. And I can do this NumPy vectorized thing and speed it up to 6 times in this case with NumPy. So here I also just used some tiny tricks, basically 2 lines of code. And it made quite a difference. So if you do heavy calculations which take days, you can sometimes basically boil it down to a few minutes or so, or a few hours at least. So, okay, another thing which is really cool and which you should keep in your mind. So I use this from time to time. It's not really something which I use all day long, but it can be really helpful in some cases. It's NumExpr. It's initially written by David Kuki. And these provide you routines for the fast evaluation of array expressions element-wise by using a vector-based virtual machine. This sounds a bit crazy, but it's really easy to understand. So here's the NumExpr usage example. So what you can see here is I created the array A, which is just this 0, 1, 2, 3, 4, and then some other array, which is just a linear, so a space, a few 5 values between 0 and 2 with equal distance. And this is how I call it. So I imported NumExpr as NE. This is a convention, and I can evaluate this expression now. So I pass in a string with the expression I want to calculate. So here I tell NumExpr to square A and to add 3 times B to it. And this will give you this result. So it works exactly like you would expect. And let's see what it brings you. So in this case, if I use NumPy, here I also took some random numbers, 1 million, and I do really complicated stuff here. And as you can see, it takes something around 80 milliseconds. And the reason it takes so long compared to NumExpr, which we will see in a few seconds, is that here intermediate arrays are created. So you can imagine that, of course, Python doesn't know that in the end you are only interested in the end result or how it could combine things together. So it calculates this A to the power of 3, this A to the power of 5. So these will create 2 intermediate arrays. They have to fit into memory again. So the computer, Python basically asks all the time for a new allocation in memory, which takes a lot of time to create these arrays. And also here, if I calculate the logarithm of A, it will also create a copy of it. So it has to ask again your memory to give it space for 1 million array elements. And then it does this 2 times, and then this minus and plus, which will also create intermediate arrays, etc., etc. So all in all, it will count up to 82 milliseconds. And depending on how much calculation you do and how much memory allocation you do, you can get a really bad performance. And this is where NumExpr is really nice. And you can even use it with multiple threads. So in this case, I set the number of threads to 4. And I evaluate this expression. And whenever you pass this string, NumExpr will see that, okay, you are only interested in this whole expression. So you are not interested in the result of A to the power of 3, etc., etc. So it does this really fancy things to avoid extra allocation. So in this case, it does it in around 8 milliseconds, which is 10 times faster. Of course, I'm using here 4 threads. So in reality, if I would use 1 thread, it would be only like I have not tried it, but it would definitely be faster as NumPy. But as I said, depending on how much memory allocation you do and how much calculations you do, it can make a huge difference. There are a lot of operations which are supported. So there are these logical operators, comparison operators, unary arithmetic operators, and binary arithmetic operators, and a lot of functions which you can also call inside. So square root, arctangents to prod, sum, even things like contains, which is a string contains. So whenever you do text processing, NumExpr might be something which you should check out, because it's really fast and it's kind of hard to get right in Numba, etc. Okay, so Pandas level is Explorer and Novice. Good to know. That's also quite nice then. Oh yeah, I forgot to ask you what kind of file formats you deal with in your daily research. Let's do this first, and then we do a little bit of poll for Astropy, so that Axel knows how much you know about Astropy for the Astropy lecture. Okay, so Astropy. The history of Astropy. Yeah, this is basically the situation in 2011 where you have some example problem like convert from a given coordinate system to another coordinate system, and the solution in Python was something like, oh yeah, you have to use PyAst, or no, just use Astrolib, or oh, there's also this astrophysics library, or PyIFM, or PyAstro, or Captain, or whatever. Yeah, so a huge discussion was started in June 2011 with a series of votes, and people said, okay, we don't want to have this segregation of all kinds of different tools. Let's build something new and try to consolidate our knowledge into basically a single framework. I would call it a framework, and this is called Astropy. So the first public version, it was version 0.2, was presented and described in this following paper. If you want to have a look, I will upload the slides. The slides are already uploaded, so you can have a look. So what Astropy is basically, it provides you a core package, which is a community-driven package, and it's intended to contain much of the core functionality and some common tools needed for performing astronomy and astrophysics with Python. So it has some nice data structures and transformations, like these constants and units and quantities, all kinds of data sets, table and times, and of course astronomical coordinate systems, models and fitting and analytic functions. It has I/O functionality because of course we use FITS files or HT5 files or other files, CSV, etc. And of course also the virtual observatory stuff. And as I already pointed out, the astronomy computations and utilities like these cosmological calculations, convolutions and filtering, data visualizations, etc., etc. So this is the core package. And oh, okay, I see a lot of CSV users as usual, custom binary formats, of course, ASCII, fits. So yeah, this means that we have a lot of Astro people here. Good to know. Okay, I go to the next poll, which is about your Astropy level. So yeah, as I said, this is the core package, and there is this Astropy affiliated packages. So these are tons of astronomy related packages. These are not part of the core package, but has requested to be included as part of the Astropy project community. So these are basically things which promise you that they are following Astropy conventions and using the core functionality. So whenever you see an affiliated package, you know that this fits really nice into this framework. Here's an Astropy example. Here you can see that you can download file with the utility function, which is already provided by Astropy, so you don't have to figure out how to download some things with Python. You can access metadata of custom formats which are popular in astronomy, like FITS. So in this case, you can print this metadata. You can extract the image data, and then you can do plotting via Matplotlib. So it's everything is connecting really nicely together. So I see that we have a lot of explorers and a lot of novice people here. So I think you will learn a lot in Axel's course lecture. And here's another example of Astropy, where you can see that I can grab my favorite Messier object, which is M13, and prints out the coordinates, and then I can convert it to our, I guess. So yeah, don't worry. We will discover Astropy in the hands-on workshop. And now let's go to something completely different. This is SymPy. It is a package which is not so popular, but it can be really helpful if you are working with symbolic mathematics. So it aims to become a full-featured computer algebra system, so-called CAS, and it tries to keep the code as simple as possible, and it basically gives you tools to make your code very comprehensible and easily extensible. It's written entirely in Python, so don't expect to have some really nice performance there, but it's totally enough for working with symbolics. And it only depends on NP math, also a pure Python library for arbitrary floating point arithmetic. So what it is for, so it's for solving equations, of course, solving differential equations. It can do some nice simplifications like trigonometry, polynomials, etc. It can do substitutions, factorizations, partial function decomposition, etc. Taylor series, so all kinds of stuff which you might need in your theoretical stuff. And here's a very small example. So if I, for example, use the base Python module math and calculate the square root of 8, and then square it again, I don't get 8 back because of this floating point mechanics. But if I use symbolic stuff like here, I imported SymPy, I calculate the square root, and this if I square root of 8, and if I square it back, I get exactly 8 because it knows that it was the square root of 8. So this is the concept of this symbolic things. It gets rid of all these floating point arithmetic stuff. And yeah, of course, much more. Here's another example where you can define your symbols. In this case, I defined X and Y, and then I have this expression which I can build up from these. So I create an expression which is X plus 2 times Y, and you can then work with this expression like adding 1 to it, then it just remembers that you want to add 1 to it. And if I multiply it with X, then it even simplifies it. You can expand it, and it's really nice. If you work with Mathematica before, you know what I'm talking about. This can be really handy for more complicated stuff. And yeah, here's yet another example. It also has nice features to give you some eye candy for IPython or also Jupyter notebooks. Here I activated the Unicode output. So I defined this X symbol, and I did this, I differentiated the sinus X times e to the power of X for X. Oh, this was too fast, I'm sorry. And you can see that it prints this Unicode stuff here. I can integrate this, and yeah, you get these nice symbols to make it more nicer to your eyes. Okay. The next one is awkward array. So I saw that there are at least a few people coming from HEP, so they might know this. So that they already know this, but this can be very helpful for other people too. So this is a really cool library which makes our lives at KM3net, at the experiment I'm working on with this neutrino telescope. Really nice. It's called Awkward Array. Jim Pivarsky from the Scikit HEP organization. It even has a dedicated website. You can go to this website and explore it if you want. So what it is first, there is a motivation. So NumPy arrays, as we already have seen, gives you these rectangular tables or tensors, and those cannot express variable length structures. So what it means that, for example, in high energy physics, you often have tree-like data, which means that you can generate events, and events have like a variable length, variable number of particles they produce, and then subparticles, etc., and then secondary things, and so on. And these stuff cannot be represented by NumPy arrays. You have to basically split it up into small arrays and then store it in other NumPy structures because they have different length. And this tree-like data, which is, as I said, very common in high energy physics, is can then be represented by this awkward array. Yeah, and I mean, you can do it in Python, as I said. You can also create your own class and do some things there, but speed and performance is really crucial. And often you have to analyze this data as a whole, and you want to do operations on them. And if you do it in a Python way, where you have your objects and an array of objects and then these graphs and trees, etc., then iterating can be really, really painful and slow. And yeah, an awkward array gives you also these nice interactive interfaces for commonly used operations like cuts and aggregations, as I told you, which I will highlight very briefly. So, okay, what is awkward array? It's written in C++ and designed to work with Python. So this is really the main aspect. It's really a Python library, but it works also in C++. And it has Numba support to take it on the next level. And this is really cool because you can construct and also pass awkward arrays into Numba jittered functions. And it offers a lot of functions to work with dragged and checked data, as I told you. Let's have a look at it very quickly. Here's a very, very small, tiny session which I made in Python. So I imported awkward as AK. This is the convention. I created an array, and as you can see, here is an array which contains subarrays of different lengths. So you cannot express such an array in NumPy in a performant way, because it's not rectangular. So it has not a shape like 3 times 4, etc. But it's basically awkward. And if I print it, you can already see that it prints it nicely, just as I defined it. And the type, so the D type, is not something like we have seen in NumPy, but a bit different. It says in this case that it's 3 times variable length, take it like this, times integer 64. So this means that I have 3 64 integer arrays of variable length. And in reality, all the stuff is stored in contiguous arrays, and it does some nice tricks with this indexing, quite similar to this reshape thing which you have seen in NumPy. So it's really efficient when you do slicing on it. So in the fourth column here, or fourth cell here, you can see that I can access the first element of each subarray just by using this NumPy syntax, which you might know, but we will explore this also later. And it works quite easily. And the array you get back has now the type 3 times integer 64. So it's a fixed type. It's not variable length anymore. So this now can be also expressed as NumPy. And you can easily pass this or convert this into NumPy array, which is a no operation, basically. And there are these aggregation functions or other functions which are utility functions. Those are mostly attached to the AK namespace. So I can call AK mean and give it this array and tell him on which axis it should operate. So as you can see in this rect structure, I was able to calculate the mean along the first axis. And this means that for each subarray, it calculated the mean and gives me back this 3 times. And there's this question mark float 64. So yeah, the question mark is probably not for this topic. It just means that it's an optional. So as I said, it supports tree-like structures. So this means that you can pass in almost any kind of things. So in these examples, you can see that here I passed in an array of tuples, and it understood that it's an array of tuples which contain bool and int64. So it's really type stable. It fits into memory contiguously. So this is not like tuples are stored somewhere in memory and pointing to each other, and then et cetera, et cetera. So it's really high performant if you iterate on those. And in the lower example, I passed in I think it's a vector of 2 dictionaries. Yeah, so these are so-called records. Yeah, it's also figured out how to represent it in a nice and performant way. So here's a very nice introduction by Jim himself on YouTube. You can just search for awkward array on YouTube and you will find it. Or of course, you can download my slides and click on this link. This is just a slide taken from his presentation, where you can see that we have event 1, 2, 3, and 4, and there is a collection which contains different lengths. This could be, for example, some hits on a PMT, and then in collection 2, you can have some other hits on some PMTs or whatever, and then you can do these join operations, and then you get these derived collections, all using these awkward array operations. All right, let's go to the next one. Okay, so we already saw this in Astropy. What is your preferred way to play around with Python? Is the next poll. So I will talk a little bit about IPython. You probably know this is an interactive Python shell. It's really much better than when you launch just Python. It has object introspection. It has input history. It's persistent across sessions. This history, so this is cool. Whenever you start a new instance of this IPython, you get your history back. It has extensible tab completion, which is really nice, and some magic commands, like you have seen these timing macros I've used to check the performance of the code is coming from IPython. It's easily embeddable in other Python programs and GUIs. So if you plan to write some GUIs in Python, it's always nice to have some kind of debugging feature where you can simply launch an IPython session and introspect things during runtime. And it integrates a really nice access to the PDB debugger. I'm not sure if you have some nice debugging session this year in the school, but I think we have. Okay, so there's also syntax highlighting, which makes it easier to make inputs, and the real multi-line editing, and it also provides a kernel for Jupyter. So yeah, and much more. So this is how it looks like. I think that many of you are familiar with it. I see that we have a lot of Jupyter Notebook users and purists with Python. So I really highly recommend you to switch to IPython at least. Or if you want to try something new, you can also try BPython or PTPython. These are also nice alternatives. But really, everything is better than this pure Python thing. So just try it out. Here you can see a session where I import NumPy. And I typed np dot, and I think I only hit F and then tab, and it automatically started to show me this tab completion. You can even see the function signature, so you can really nicely do this exploratory thing and find out how things work. The next thing is, of course, Jupyter. This is an open source project that offers a set of tools for interactive and exploratory computing. It's born out of the IPython project in 2014, and it provides you this console and a notebook server for all kinds of languages. Many people don't know, but Jupyter is basically this combination of the three main languages which it supported at the very beginning. It's Julia, Python, and R. And as I said, it gives you this easy way to explore and prototype things. Many of you know this, so I will not talk too much about it. It has support for Markdown and LaTeX-like input and rendering, and it allows you to share code and analyze results. And yeah, there are a lot of extensions which you can install. So it's really nice. There's also this console. So if you run just the terminal frontend for kernels, so you can use this console to launch it. It will basically launch IPython in this case. Here, this is a very old slide I'm showing. That's why you see Julia 0.5 and etc. But yeah, you can use multiple kernels. I can run Haskell also, and then Python stuff, and then Julia stuff, and all kinds of languages are supported. So it's really nice. Yeah, I think sorry. All right, here's the kernel with Julia, and it looks the same. Okay, so now we are at the web-based applications. Sorry, I got just some technical issues on my computer. Now it works. Okay, so here's an example of a Jupyter notebook, how it looks like. And when I'm doing my analysis, so these are just really old things which I'm showing here, but just to show you how it would work. And you have the cells for code and markup input. You have rendered output images for text, images, and tables. And there's also this JupyterHub thing, which you might know. This is the next level of interactive in notebooks. It combines terminals and text editors, image viewers, table viewers, CSV viewers, all kinds of viewers are there. It supports editing multiple notebooks at once, which is really nice. And it has drag and drop support to arrange panes, which is cool. So here you can see me at work a couple of years ago. You can split your screen, and you can also launch your IPython session at the bottom, and you have your file browser on the right, and you can extend it with a lot of stuff. So this is really cool. If you are working at your university or so, you might have heard about this JupyterHub thing. This is really cool. It basically creates a multi-user hub, which can spawn and manage and multiple instances of Jupyter Notebook servers. So this is also a nice environment for teaching. So you could ask your IT admin to set up such a server so that you have a central place where you can log in and use the data. Many computer centers already offer this. So if you're working on batch farms or some computing centers, you might have heard about it. But if you plan to do some works with multiple people on the same machine, JupyterHub is a really nice option. That's why I wanted to mention it. All right, there's another thing which I like. It's called Interact. It's an application. It's a standalone desktop application for developing computational notebooks. It's basically a viewer for Jupyter notebooks, and it integrates into your system and file browser. So this is really cool because often you have your Jupyter notebooks on your on different folders on your machine. And you always have to go to your browser, type in the address and your port, so local hosted port, etc. Or of course you have your bookmark linked or whatever. But you always have to use this navigation folder navigation system of Jupyter. And what Interact gives you is it's basically an application where you can just double click your notebooks, or on the Mac you just hit spacebar to preview them. And it launches this Interact, and you can quickly look at notebooks. You can even edit them. So it discovers all the available kernels which are installed in your Jupyter instance, and you can even use them. So this is how it looks like. You can see that this is just a Jupyter notebook which I launched with Interact, and it looks a bit different, but it works the same. I can here edit the code, I can launch it, and here on the lower left, you can see that it's running on a Python 3 kernel. So there's a menu bar in macOS and also Windows and Linux where you can open other notebooks or switch the kernels. Yeah, so it's a nice have in addition. Okay, and now coming to the end, slowly but surely, there are some other nice useful libraries which I just want to mention. There's the Seaborn. This is a statistical data visualization thing which uses Matplotlib as backend. So you can see it as an extension to Matplotlib. It gives you some really nice high-level functions to do some very common statistical plots. So here you can see that you can do a linear regression with just a single command on a data set, and do a lot of work with less commands, and also the appearance is really nice. Here are some wrapper functions for Matplotlib. Here's a join plot which shows you this nice histogram. And yeah, I think we will see some examples, but just to mention that there is this tool, and it's easy to use and nice to, and it also works really, really nicely together with Pandas. Another really nice tool is Docopt, which creates beautiful command line interfaces. So as a scientist, you probably want to write some command line tools at some point, and this can be really painful. So if you look at the argparse, optparse functions or how to use them, I always have to open the documentation and look things up because I cannot remember this. So there are so many classes and so many functions, default values, etc. It's really, really hard to memorize. And the idea of Docopt is that if you have a description of a tool like this, so you have some kind of, this is the example of the Docopt homepage, you have some kind of description at the top, then you have some usage examples, etc., and you define your options. This is basically what you get if you do something like command -h, or if you're on Windows command and \h, or question mark. This is what you get displayed anyway. So if you write an application, you want to have something like this. But if you already have this already defines how your application works. So this is what Docopt took. So it said, okay, let's put it in a string, in a doc string. So if this is my Python file, you can see that I put it on this shebang line at the top that represents it as a file. And then I start with 3 triple quotes. So this will interpret it as a doc string of the file, which you can access in Python as __doc__. Then I can call Docopt if I import it. And I parse this doc string, and I get back these arguments. And what you get from that is if I launch this program now I'll fade with these arguments, then my arguments will look like a dictionary with all the values, whether they are set or not. So if you see, as you can see, speed is set to 20. So you can just grab out the value of arguments if you provided the string speed, and you get back this 20, etc., etc. So this is really cool. It works out of the box. You only have to write your help string, which you have to write anyways at some point, and then it parses everything from that. So I really love this. I use it a lot. I use it basically in every kind of command line application. The only thing is that you have to take care of types. So as you can see, the speed is here passed to you in the dictionary as a string, but you want to have it an integer. So there you have to do some type checks or type conversions sometimes, etc. And for this, click is something which you can use if you want to have some more major command line utility interface. It's much more advanced compared to Docopt, and should be the number one choice if you really want to go crazy with command line utilities. Here you can basically decorate, so kind of similar to how Numba works. You just put these decorations on top of some functions, and they are then converted into command line functions with default values. So as you can see, this hello command will become hello, and you can add an option --count with a default value and the help messages, etc., etc. So if you call this in the command line, it will also give you these help messages and provide you this string, which I showed to you before. Okay, so we are approaching to the end. So what now is the question? Let me transfer to the last poll question. So my final personal thoughts. Yeah, so I spent a lot of time optimizing Python code in the past years. So I worked with all these libraries extensively, and I wanted to share a short summary of my personal experience. So there were several attempts to make Python itself faster with respect to low-level programming, and none of them are really satisfying. So you have this SciPy, Python, etc. Many of them were abandoned. This is quite sad, because it's really hard to get Python fast. You always have to interface to other languages. I would advise you to think twice before you bake something like Cython or any other static compilation into your project. So if you want to make things fast and you incorporate with another language, it will be really hard to maintain. So this is called the two-language problem. It is real, and it's really hard to get it right. So the performance gain is often disillusioning compared to the work and workarounds and mess one needs to deal with later on. So, and you also need a lot of know-how. So you often have to understand Python fully, and also, for example, C++, etc. So keep in mind that this is a lot of overhead. If you look at the code, for example, for R-quad array, which is written by a very, very experienced programmer, Jim Pewarski, you can see that it takes a lot of effort to make it really nice and work together with Python, and also Numba and NumPy, etc. So me and my lovely dev team made the best experiences with Numba. So there's no clutter or double bookkeeping and no static compilation. This means that you have really basically minimal dependencies. So if your project is not really huge and dependent on a lot of different stuff, then Numba might be your best friend. And it's often really orders of magnitude faster than other low-level algorithms utilizing custom Cython class or instances of C types or whatever. There is finally dict support since I think 1.5 years or so. Dictionary support was not there, and it was really a pain to implement things fast, which are somehow connected to dictionaries. And the downside, of course, of Numba is it's super slow if you don't have it installed. So if you build your whole package upon Numba and you pass it to someone who, for whatever reason, don't have an LLVM compiler or cannot run an LLVM compiler or whatever, then everything will be super slow. So this is also downside. Yeah, and a general advice when it comes to high-performance coding using Python, you mostly have to think in NumPy arrays. The bad thing is you really cannot easily model your own data types, like example in C or C++. You can do these fancy D types, which we will have a look later on. But what you can use if you have some awkwardly structured data is this awkward arrays. So that I highly recommend if you want to make things faster, which are more ragged and jagged, then awkward arrays offers you now a really nice way. Okay, so and my receipt for high performance code is you should avoid massive amounts of Python class instances. So I've seen code where people Of course, you always, when you learn object-oriented programming and you see, you create a point and the point has an X and a Y attribute, it's really nice. Then it's very tempting to create your own Python class of a point and then make X and Y, etc. And then create millions of instances of it, but then you completely spam your memory. So this will never be fast. You should always think in Python classes which are more high level. So instead of creating a class for a point, create a class for example, a set of points or something like whatever, which holds then NumPy structures or other structures which are efficiently stored in memory. So that's why my second advice is use NumPy arrays for large homogeneous data or awkward for rect data. So as I said, instead of allocating millions of points or instances of points class, just create a 3 times n NumPy rec array instead, where you can also access points.x and points.y and points.z, etc. So this also gives you this nice syntax, but at the same time, it's using these nice contiguous arrays in memory. Vectorization is a good idea most of the time. So vectorization means that you do operations on arrays. There are tools for it to create vectorized functions. And you should try to reuse already allocated memory. So whenever you want to modify an array and you don't need it later, then you might do some in-place allocation. So a very dumb example would be a large array and you only want to add some numbers to it, then add it in place. You can iterate through the array and modify each element in place, so you don't have to reallocate and calculate another one and put it into memory, because as I said, allocations are expensive. And second last, always profile first before you do heavy optimizations. So all of us have already spent, I think, time on optimizations, and at the end they figured out that it gives you like 1% or so. So this is always good to first profile your code and see where your code is slow, and then try to make that huge chunk which slows down your code first fast. Often it's not the place where you're looking for, where you have to optimize. It's really funny. Also for me, as an experienced programmer, I sometimes overlook things, and when I do the profiling, I'm really surprised that specific line of code takes a lot of time, or a lot of memory, etc. So you can often discover bugs this way, and in your code or other libraries, etc. So yeah. And there's this nice premature optimization is the root of all evil from Donald Knuth. You might know this. But keep in mind, it doesn't mean that you sit down and tag together whatever works. This is not what Donald meant. You should always take care of the basic principles, like the example above. Don't create 10 million points of Python classes, etc. And of course, last but not least, don't reinvent the wheel. You will mostly find a library which does kind of what you need, better, faster, and for no cost. So start first there, and if you reach the limits of that library or code, maybe try another one, or just try to contribute, and don't fear about it. You can always discuss with the authors, and it will make the code better. If you find a specific example which is not covered, or a specific use case which is not covered by a specific library you've found, then just extend it. So this should really work. Okay, and one more thing. The last one, example why it's so hard to make Python fast is you may have wondered why you can't put Numba on every single function. Well, there is this crucial aspect in Python that Python basically lets you do anything. So you can here, if you look at a pure function like this, square a number, and it returns a float to the power of 2. So in this case, I'm using this built-in float. So you might think this is untouchable. If I pass this to Numba knows that this float is definitely fixed. This will create a float and take it to the power of 2. So it will pick the right command of your CPU or right execution command of your CPU and create a really performant machine code for it. And every decent compiler should be able to optimize this code using this function. With all the things it knows, like repeated calls, tail recursion, elimination, inlining, etc., etc. But you can basically import built-ins and modify this float to point to int. And this is something which can happen during runtime, and this makes it very complicated. So Numba has to check, has this function changed? What is now the return value, etc.? Is it even type stable? It has to recompile it again because it doesn't know it. So yeah, this can make the life really hard to optimize code. This is also the reason why it's extremely hard to make Python code fast, and this is why we have this two-language problem. All right, that's it. I'm not sure if you have time for questions, but maybe we can do them later.
Okay. So thanks a lot, Tom, for this nice overview of all the libraries. Okay, I'm just looking forward to the really deep courses, because I mean, I'm sure that, well, I mean, if with this one we have already learned a lot, I don't want to think what's going to go with the deeper courses. Okay, so there are a couple of questions that I will go through them. So okay, there's one that says mainly all about Numba. So okay, just a quick reminder, on next Monday, there's a course, a lecture about the optimization and Numba a bit, about that it will be given by Carl. So okay, that's just as a quick reminder. So one of the questions says, although you have quite explained in a bit now, it is like, if Numba is so fast, why it isn't implemented used by default by Python?
Yeah, so this is basically what I said. You cannot do it all the time, and also Numba has limited features. So some things cannot be optimized by Numba. And in this case, Numba will fall back to Python mode. So you usually don't want to run something on every function call, because in Python, if you launch something, a lot of functions get called. So if you put an overhead on each function, and Numba always have to see, okay, can I somehow optimize it? If not, then pass it further, and this will slow down your application. And you will experience a lot of problems when you try Numba, because it will often give you an error like, oh, I don't understand this structure, or this is not supported, etc., etc. So it's really, Numba usually works for very low-level things. So you really have to write your loops, etc. You don't use class instances inside Python, inside Numba functions usually. So it's a bit tricky, everything. So that's basically the main reason.
Okay, perfect, thanks. Also, there was another one saying, like, if I understand correctly, Numba only works with vectorized datasets. So does it work with serious datasets like mathematical expressions only?
Well, it all boils down to mathematical expressions at the end. So the CPU always does these low-level function calls. So not sure if I understand correctly, but even if you do text processing or so, at the very end you are fiddling the bits around. So Numba can make this also faster. But as I said, there are things which cannot be inferred as so type inferred. This is how it's called in Numba, and this is where you don't gain any benefits. Hope this answers it.
Okay.
Otherwise, we can of course chat about it in Slack later.
So yeah, there was another question on Slack, but it is nice to raise it here. So can Python distinguish between can Python distinguish functions imported from different modules but having the same name? So let's say mathematical functions from NumPy and the other one from SymPy.
That I'm not sure if I understand. If you import something in Python, and you import something else with the same name, then it gets overwritten. So yeah, that's it.
Yeah, exactly. So
we usually do this namespaces thing. So if you remember the Zen of Python, I think the last one is namespaces are good. Let's use more of them, or something like this. So what you usually do is import NumPy as NP and import NumPy or another library as blah, blah, blah. And then you have this namespace. So you will not confuse names with each other. It's not a good thing to pollute your global namespace with things. Like don't do something like from blah, 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 import sign or so, and then use this sign function because yeah, it's.
Yeah, perfect. Thanks for the answer. And okay, last question that I will just ask also about Numba is how it is possible that Numba runs so much faster when it has so many intermediate steps to do.
Okay, yeah, that's something which we will definitely explore in the Numba session, I guess, next week. You will also see some Numba examples today. So what you have seen, what I showed you with this procedure where the code is compiled and lowered to Numba intermediate representation, then the type inference, and then the LLVM intermediate representation, and then finally the compilation, only happens on the first call with a specific argument type. So whenever you have a function which you number decorate and you call it with some value, like for example an integer, Numba sees that you have called this function with an integer and then does this type inference for every single thing which is calculated inside this function. And this creates a compiled function, and this function is cached. So whenever you call the next time this function with an integer, it already knows that it did the type inference for this specific type of value you passed, and it will reuse the cached function. Whenever you call this function with a float, for example, or another type which it has not inferred yet, then it will recompile the function with a new type inference. And this is why it always takes time on the first call with a specific type. So the first time you call a function, a number decorated function, you always have the compilation time. So I will show it to you later that the first time is always really bad, like it takes several hundred milliseconds until it's compiled, plus the execution time. And the second time is then really just the execution of the machine code.
Okay, perfect. Thanks a lot, Tom, for answering. Okay, so we're going to close this session here. Now it is coffee break time. So we are going to return. We'll be back in 25 minutes, 22, a bit more exact, at 11 o'clock. Okay, so thanks a lot, everybody. Thanks once more to Tom, and see you in a moment. Bye-bye.
All right. Thanks. See you later. Bye-bye.